So how many of you are computer science majors?
A lot of it.
Wow. The math club talk might be of interest to you this week. It'll be Friday, 5 o'clock right over there in 102. We have a new faculty that does a lot of coding theory. It shows up in computer science quite a bit. Talk about error correcting codes and security. It might be kind of an interesting excursion for you. So I encourage you to be there for that. So today we are going to talk about we're going to talk about the inverse matrix. And actually, we'll see an application today, but there will be a lot more applications that you see as we go on. Let me put a caveat here. So if I walk up to you on the street and give you a matrix, it may or may not have an inverse. A necessary condition for it to have an inverse is it has to be a square matrix, right? None of this crazy rectangular stuff. It always has to be a square matrix. But even square matrices do not necessarily have inverses. And we will be studying a lot of this as we move forward. Let me ask you this. This is kind of a simple question. If I just give you a number and say, what's the inverse of 2? What would you say? 1/2, right? It's the reciprocal. The notion of an inverse is basically the notion of reciprocal generalized to matrices. So this generalizes the reciprocal, the inverse of the number. Now, let me ask you this. I happened to write 2 up on the board and said, what's the inverse of this? You said 1/2. I have to agree with you. What number could I put up there if you couldn't answer me? Do all numbers have inverses like that? Name a number that I couldn't find the reciprocal of. 0. Zero's got a problem. The zero matrix, analogously, will not have an inverse, but even more generally, other matrices sometimes do not. So, let me get to this by saying definition. Let A, and let me emphasize in matrix. So, as I said, for us to even be discussing this, it has to be a square matrix. We say A is invertible or non-singular. Sometimes you hear this terminology as well. If let me see if I can finish this idea. What is the inverse of a number? Well, what was the inverse of 2? It was 1/2. And how can you tell that 1/2 is the inverse of 2? What's sort of the defining characteristic of 1/2 being the inverse of 2? You multiply them and you get 1, right? That's what it means to be an inverse, right? The inverse of 17 is 1/17. Multiply and get 1. So, what do you suppose the inverse of A, when you multiply 2 in by n matrices, you're not going to get a number anymore. What do you suppose this means? Good. The n by n identity. And the lawyers are going to make me this because I want to make sure that you multiply together to get the identity matrix on both sides, because one of the things we've seen is sometimes multiply matrices in 2 different orders, you don't get the same answer. Right? However, it turns out we do put inverses here. So this is all it means. Let me use some terminology to go with this. If such a V exists, it is called the inverse way. And sometimes we write it this way. Right, this way. If A is invertible, it's called singular, as I mentioned earlier. And if not, it is singular. So a singular matrix is just one that you can't find an inverse. Let me give you what you saying. Okay, question. Is this thing singular or not singular? Anybody want to take a guess? I'm going to set up some equations and show you the power of linear algebra here. But anybody want to take a stab at this? What do you think? Singular or not singular? Okay. Clues. What makes you think that?
It's like 1 and 2, and then 2 1 and 2 times.
Ooh, the force is strong with this one. That's right. The second row is a multiple of the first, right? And that's actually kind of trouble. We're going to see that later. Okay, let me just get hardcore and try to write it down. Let's try to build a matrix. So if there is an inverse, I have to be able, so this is my fake inverse here. When I multiply this by this, I should get the identity, right? Everybody agree? And this just gives me some equations to solve, right? So let's see what I can do with this. Well, actually, I'll take this step here. Let me multiply these two matrices here. What do I get here? This row times this column, I get A plus 2C. And this row, this column, I get B plus 2B. Right? This row, this column, I get 2A plus 4C. And this row, this column, I get 2B plus 4B. Okay, so let's suppose that I can solve this. Well, just kind of pair things off. I get A plus 2C should be 1. And I get 2A plus 4C equals 0. Now, by the way, I've got two other equations I can write down too, right? All I did is I just messed with the first column. That's going to be all that I need. And we'll see that your idea was exactly right. Because how can you manipulate this equation? What's an easy thing to do to it? You divide by 2, right? So this becomes, and this is a blatant problem, right? Because A plus 2C is 0 and A plus 2C is 1, there's no solution. Right? And this worked exactly because, notice this is a multiple of this. So this is an example of a matrix that's not full of zeros, not all zeros, and it is single, right? It has no inverse. Okay, questions on this? You might ask yourself, is this what you need for like one row to be a multiple, another for the matrix to be single? Yes, with 2 by 2 matrices. Larger matrices, it gets more and more complicated, the bigger the matrices. And in fact, I can give you the following theorem. I'm going to get all 2 by 2 matrices lit now. I'm going to take care of all of them. Theorem. But so this is obviously, I'm just talking about 2 by 2 matrices here, and that's it. Suppose that this times this minus this times this is not 0. Then A is invertible. And I can tell you what the inverse is. Matrix B minus B minus C. So in other words, what did I do? I took the diagonal entries and flipped them, and then I changed the sign on the off diagonal entries, and I multiplied by 1 over this number. You know, math always takes care of it. So let me make a couple of observations before I stand ahead. But first of all, let's assume my formula here is right. You see that this is going to be a problem with AB minus BC and 0, correct? That's one fallacy. Let's also look back at our example that we did before. That, you know, she noticed that one of the rows was multiple of the other. What happens if you do AB minus BC here? You get 4 minus 4. So you can see. Let's check if this works. So by the way, if you like, another way to write this matrix is this way. Remember, this is just a number times a matrix. So this is B over AB minus BC minus B over AD minus BC minus C over AD minus BC and A over AD. That's another. So for example, actually, interesting. So in this case, AD minus BC is 3 times 1 minus 2 times 2, which is negative 1. And so if I trust my formula here, A inverse is equal to, see what I do, flip these two, 1, 3, minus 2, minus 2. Right? But I have to multiply this by negative 1. Right? The negative 1 being this thing right here. Everybody okay with it? So this should turn out to be -1, 2, 2, -3. And that works. I'll let you verify that that won't plus the identity, because I want to do something more general. Suppose and really, the only thing that this assures us is the fact that there's no zero denominator. Let's see what happens when you multiply this. So I'm essentially going to prove this, but it's not really proof, it's really like computation. C A Okay, let me try to make my computation a bit easier. Would everybody agree with me for a moment that when I multiply any row times any column, I'm going to get some crappy fraction with AD minus BC in the bottom? Everybody okay with that? So I don't know much, but I'm going to have AD minus BC in the bottom of every one of them. Everybody okay with it? So all we got to do now is figure out what the numerator is. So what is the numerator here? This row, this column, numerator is AD minus BC. Okay. Here, this row times this column, numerator minus AB plus AB. Second row, first column, CD minus CD. And finally, second row, second column, minus BC plus AB. Everybody okay with that? And look what miraculously happens. What is this one? It's a zero because you got a zero numerator. Same here. And these, as long as that denominator is not zero, these are clearly one. Right? This is AD minus BC. So the formula works. But okay. I can't give you a formula for 3 because I mean, you could derive one if you're like, really love math or you're masochistic or whatever. But it gets more complicated. I mean, the 2 by 2 is the easiest. We will, for larger matrices, I'll give you sort of different formulas using some other things that are similar to this, but they get a little bit too complicated right now. But the 2 by 2 case works out very nicely. Let me make a note on all this. Obviously, there's an important number floating around here. Then the number A minus BC is called the determinant. And it's a special number because it tells you, I mean, that number by itself just tells you one important thing, and that is that, well, it tells you if the matrix is singular or non-singular. If the determinant is zero, the matrix is singular. If the determinant is not zero, the matrix is not. It's inverted. Again, there's a notion of determinant for any square matrix, no matter how big, but I'll have to show you later how to do those. Yes.
Why does AD minus BC need to not equal 0? I understand why it does for that formula, because dividing by 0 would be invalid. But why for inverting in general does AD minus BC need to not be 0?
Well, if there is an inverse, it must be in that form, which forces AD minus BC to not be 0. And another answer to your question, yeah. So if there is an inverse, it has to be in that form, which means that your denominator can't be 0. Number two, if this turns out to be 0, you can set up a system of equations to show, just like we did in that example before, that you can't solve. All right, so it's similar to that first example. Okay. Here is the first theorem, and I'll show you an application of this. And this application, you might dismiss as kind of silly because there's other ways to do it, and why we're doing it this way. But this application is actually very, very important to bigger matrices. So the larger your system of equations are, the more useful this theorem would be. Yes. A is, we'll say again, square matrix. So our playground of square matrices here is invertible. Then we'll call it B. The equation S equals B. A unique solution. Okay. I'm actually going to show you that this is true. This is section theorem. This actually says two things. Remember, this matrix equation was very fundamental, just from the point of view of matrix itself. And also, this is what we get when we get a system of equations. We can put it into that matrix form and find the augmented matrix and all this. There is a restriction here, and that restriction is we're assuming that A is an n by n, so it's a square matrix, right? So if you think of this AX equals B as a system of equations, then it's a system. You've got n variables and n unknowns and n equations, right? So you get the same number of variables. In my proof, I'm going to tell you exactly what the solution is. Anybody, can you tell me what the solution is? So I'm going to prove this, but this is going to be computationally useful. Then the solution. This is the whole point of the inverse. The solution is just take the inverse of the matrix A and multiply by what B is, and that barfs out your solution. Bang, like that. Okay. This theorem actually has two parts, even though it doesn't look like it. Number one, the theorem says there is a solution. I can solve this. Number two, it says the word unique. So that means my solution that I get, that's it, baby. There's no more solutions. Right? Okay. Watch this work. We show you if this works. Plug it in. A, let X be that solution. This is now A inverse B. And what is A inverse? It's the identity, okay? And I'll say in by n identity. And what happens when you multiply the identity by any vector? What do you get? How about that? So it works. When I plugged in that value for X, I got B. Hooray, hooray. Right, okay, so far. Now, number two, I want to show that it's unique. That is, so this solution exists, it works, and now I claim it's the only one. Suppose that I've got two solutions. Suppose A times X is equal to B vector, and A times Y is also equal to B vector, right? I want to show that X and Y have to be the same thing. That's what it means to have only one solution. So these two animals better be the same. That's what I need to show, right? Okay. Subtract these two equations. And I have AX minus AY is equal to what? 0. B minus B is 0. Now, how about this? Right? Right. Now, I am going to multiply both sides of this equation by A inverse. I'm going to smack that with A inverse on both sides. So I get A inverse A X minus Y is equal to A inverse times 0, and anything comes to the 0 vector is going to be 0. But what's this? A inverse A is also the identity. And so I get X minus Y is the 0 vector. So the two solutions X and Y are the same. So there is a solution, and that's it. Okay. Any questions? Yes.
Would there be another way to prove that it's like a unique solution by looking at like the number of pivot columns somehow?
It's equivalent to all that. In fact, I'm going to drive you bananas tomorrow because I'm going to give you like 12 equivalent conditions for what it means for matrix to be invertible and pivot columns. That's one of the things you can certainly look at. Okay. Other questions? Okay, so let's apply this. Let's actually do a 2x2 system with two equations and two unknowns. See what it shakes out. We'll do this from the matrix point of view. Solve the system. Three X. So let's do the system of equations here, right? Now, admittedly, this is kind of silly because this is something you probably could have done in high school, right? You eliminate one variable, plug it in, and do your magic, right? But I want to use this matrix idea to solve this. And even though you might not bother to do it for this in general, this is showing you how the machine works, because the same thing will apply to systems of 4 equations, 5 equations, and so forth, where it's not so easy to substitute out. But sometimes it's easy to compute depending on what the matrix looks like, you can get the inverse of the matrix. And by the way, I'm going to show you how to do that number two. So in this case, we have. So here's the roles that everybody's playing. X is the vector X, Y. B is the vector 7, 4. Right? That's what things are equal to. And the matrix A is, what is the matrix A? 4, 3, 3, 2. Now, of course, the first thing I've got to ask myself is this matrix invertible so I can use all this stuff? But in this case, the determinant of A, so that's my little notion of determinant, is 4 times 2 minus 3 times 3, which is -1 again. And so A inverse should be -1 times the matrix which should be the matrix 2, 3, oops, sorry, minus 2, 3, 3, minus 4. And that was right. Yes.
So, even though it's one of the determinant, it's still -1.
Right, because 1/-1 is still negative. Everybody okay with that? Okay, so if you know the inverse, if you look back at what we bothered to do when we were doing proof computing, our solution should be A inverse. So let's see what happens here. This is -2, 3, 3, minus 4 comes to vector 7, 4, I believe it was. And this becomes vector -14 and 12 is -2. And that's 21 minus 16 is 5. So interpretation. And you can test and see what this works. But right, the magic of this is the solution can be spit out automatically by multiplying the inverse matrix A inverse times a vector. There it is. 2 questions. Okay. Let me give you one more theorem concerning sort of properties of inverse matrices. And after that, I'm going to actually develop a little bit of stuff and show you actually how to compute the inverse of every matrix. And actually, it'll also give you a way to sort of tell if it's invertible as well. So first, the theorem. Suppose A suppose that you have an inbinding matrix that is convertible. Okay. Suppose that you have an invertible matrix. This first statement says the inverse, there's only one inverse to any matrix that's invertible. You can't have two inverses. Two, A inverse is invertible. With inverse A. Number three, this one's big, because this one, maybe defines your experience, but actually it's more natural. Anybody want to guess what the inverse of AB is? Let's suppose they're both. So A and B are both invertible. Otherwise, it makes sense. Anybody want to guess what the inverse of AB is? If you want to take a guess, the behavior, this is sort of like transpose.
Inverse of A and inverse of B.
In the other order. It's actually that. And I'm going to show you why is it first. I'll show you that. Or a transpose. A transpose inverse is the transpose of A inverse. Okay, I'm going to do a couple of computations to kind of show you why this is true. Suppose that A has two inverses. Suppose B and C are two inverses. I want to show that B and C have to be the same thing. They can't be different. What does it mean to be inverses of A? This means that AB equals BA is equal to the n by n matrix. And it means AC and CA are the n by n matrix. Right, okay with that? In fact, it probably took me more just to write that down in this particular connection. This almost seems a little slimy. If I agree with you. So multiply on the left by C. And what's C times the identity matrix? It's just C, right? Do I agree with you? But this is also equal to CA B, right? Because I can move parentheses there. And what is CA equal to? It's the identity. So this is INB, which is B. So B is equal to C. So yes,
If AB is equal to BA, then why does the order of operations matter when you invert them? For number 3 there.
because in general, the reason that AB equals BA is because their product is the identity. There's no guarantee that the product of AB here is the identity. Right? Because look, AB is the identity. Nobody says here that AB, this AB is the identity. Right? It is true that if A times B is the identity, then their order doesn't matter. But in general, if you just pick two invertible matrices and multiply, then order probably does matter.
Yeah, I didn't know that that was just a condition you were laying out for the problem and not like an actual.
This is so the condition of the theorem are just that A and B are invertible matrices, and that's it. Right? This is part of me demonstrating. Okay, I'm not gonna go through that. That was pretty easy to show. Let me show why this is true. Let me point this out. What happens if you multiply this by B inverse A inverse? What happens to these two B's in the middle? It's the identity. So if I multiply AB by B inverse A inverse on this side, I get the identity. What happens if I do it the other way? You have the same sort of accordion trick. So when I hit AB on either side by this crazy matrix, I got the identity, right? And there's only one inverse, right? That's what we proved in part one. So the inverse of AB has to be this way because it works and there's only one. And for those of you that are interested in that, think about why this is true. But a key here is A times A transpose. If you take AB transpose, it's B transpose, A transpose. See if you can figure out what that's true. Because I want to get to the algorithm finding. So let me kind of spit this out at you and use it, and then perhaps explain why it works. Fine. A inverse. Yeah. It's perfect. What you do is you make an augmented matrix this way. Right? Take whatever your A is that you want to find the inverse of, right? Take this and row reduce A row reduce what's over here on the left to the identity. So do a bunch of row operations until you get IN. If this can't be done, A is single. So if you start this process and you realize after a few steps that there's not enough pivots or that you can't reduce this to the identity matrix, then it's singular. It can't be done. There's no inverse. But once you do this, if you do the same operations here, you get A inverse. This is a fairly simple process. And so let's do an example. Let's take this matrix here. Let A be 1. And we'll all go through this version, but I didn't make any mistake beforehand. We didn't do it. Okay, so what do you do? Okay, I want to figure out what the inverse of this is. So I'm going to pop it into this kind of augmented matrix. 1 minus 1, 1, 2, 0, 2, 1, 3. And then on the other side, I'm going to have the identity matrix. In this case, 3 by 3. Now, what I want to do is I'm going to start doing row operations to turn this to the identity. Now remember, this is one big row, so whatever I do here, I've got to do on this side as well. So let's get to it. Okay, so I'm gonna multiply this by -2 and add it here. So I'm gonna be 0, 2, 0. And over here, multiply this by -2 and add it down here. 2. And I'm gonna multiply this by -1 and add it down here. And that's going to be 0, 3, 2. Multiply by -1 bottom. Now, I'm gonna, just to save me a lot of writing, I'm gonna take this middle row and I'm gonna multiply by 1/2. Am I okay with that? So I'm gonna sweep through all this. So my apologies for this. I'm gonna turn this to 1. I'm gonna turn this to -1 and 1/2. Everybody okay with that? Now I'm going to take this one right here and use it to eliminate what's above and below. So I'm going to leave the middle alone. -1/2, 0. Okay, so to fix this, I'm just going to add the top. The straight up add, that is 0, 1/2, 0. And I'm going to multiply by -3 and add down here. Multiply by -3 and add it down here is 2 minus 3/2. 1. Right, okay. And now, actually, I'm going to do this again. I'm going to cut this bottom row in half. So that's going to be 1, 1 minus 3/4, and that's going to be 1/2. And it looks like I'm almost there. So it looks like the final step, all I've got to do is get rid of that shaky 1 over there. So I'm going to 0, 1, 0, 0, 0, 1, 2, -1, 1/2, 0, and 1 minus 3/4, 1/2. And really, at the end, all I have to do is multiply this by -1 and add it to the top to get 1, 0, 0. And that is going to get me, what I multiply by -1, -1. That's going to be like 3/4 and 2/4 and 5/4. And finally, minus. So in particular, A inverse for this case, for the original matrix is this. 4 minus 1/2 minus 1 1/2. 0, 1 minus 3/4. Okay. Question, does everybody understand that procedure? What we did? Now, lucky us, it turned out this matrix actually did, its row reduced echelon form can be brought to the identity matrix. This can't always be done, but if it can't be done, you'll get stuck at some point, and that means that the matrix is actually singular. All right. So let me give you do y'all remember the formula that I did for the 2x2 matrix? A good practice thing would be start with a 2x2 matrix A, B, C, D, and do this process and see if you can actually derive that formula from that point of view for the inverse. Any questions? I have one more question for you. Why does this work? Does anybody know why this works? So I just kind of made up some things. I said, do this hocus pocus, turn this into the identity, and the other piece that comes along with the inverse. See if you can think why that works, and we'll talk about that next. Any questions? All right, y'all have a good one, and we'll see you on Friday. Your next quiz will likely be posted probably this afternoon.
What do you do Friday?